Ça marche? Okay, good. So, welcome back, everybody. I'm very happy to see you here again and to start the second part of our today's session on our workshop, where to be honest, I do not have the full name in my mind right now, on sustainable video communications. I remember the abbreviation, so SAVIC. So welcome, everybody. I'm very happy that we will have three highly prestigious speakers today. And we will begin with Pierre-Luc Cabaret, who will be talking us and who will be presenting results on low-power VVC decoding with OpenVVC, not OpenHVC. Please, Pierre-Luc, if you could come here. Happy if you take the lead, if you take the stage, and I'm looking forward to your presentation.
So, thank you. So, hi, everybody. Thank you for having me here. So, I'm Pierre-Luc Cabaret, as you were just told. I've been working in EOTERA INSA for a few years now with a field of interest in video coding and most especially video decoding. So I've been working I've been involved with OpenHVC, which was an HEVC decoder back at the time, and I've been leading the team towards OpenVVC, so VVC, the last MPEG standard of video coding. So what I will be presenting today is a result of what we've done in order to make OpenVVC low power. So this is the work of the team. There was Daniel Ménard, which is here, Wassim Hamidouche, and the developing team, which was myself, Ibrahim Farhat, Guillaume Gauthier, and Thomas Mestoy. So in this presentation, I will speak about how did we make OpenVVC a low power video decoder. But just before that, just a little bit of context. So there has been a rising interest in video transmission analytical cost. So results, estimation results are a bit controversial for most of it, but what we can say is that its video consumption is growing, and it's got a pretty big impact in terms of greenhouse gases emission. And given the video consumption trends, it's not expected to go lower. So what is video streaming? Basically, we've got emission of video, and it goes through various stages. So we first acquire video, then the video is coded, and it's prepared for transportation, and then it goes through networks up to the receiver, which decodes it, which extracts the bitstream, decodes the video, and finally sends the pictures to the display. So in all those three layers, there are many devices, different devices and different technology which might be used. So, and those technologies or devices uses very different magnitudes of power, so which make the video estimation, the video consumption estimation pretty hard to make. So another problem is the variety of usages. So you've got different usage. Basically, you've got VOD, live broadcast, or video conferencing. What's important to note here is, I hope that if a video is transmitted, there is someone actually watching it. So what we hope is that there are more users at the receiver side than at the coding side. And based on this fact, we think of benefits we can make at the receiving side can scale to the number of users. And so small benefits will still matter because it will scale to this number of users. So on the receiving side now, basically most device contains hardware decoders, which is great because the cost, the consumption is low. But the issue with devices is that it's not replaceable. Hardware is not replaceable into the devices. So when a new technology arises, which has been the case with VVC as an example lately, you have to change your device in order to get access to the technology. So this leads to obsolescence, and the issue with this is that most of the time production seems to be the cause of more greenhouse gases emissions than its actual use. So here is results taken from a study or an article by Emily Graham in May 2021, saying that production was responsible for 80% of greenhouse gas emission per phone on an iPhone 8 model. So here comes the advantages of software. Software consumption may be higher, but it's faster to develop, and finally, we don't have the need to change the device because it's easy to bring new software into your device when a new technology comes. So here is problematic. What can we do to lower energy consumption of software decoders? So to answer that, I'll go through a few stages. So first, I will tell you a bit about VVC decoding. Then we'll see on modern CPUs what we can do with software in order to decode to make our decoders consume less power. So the main idea behind this presentation is that if we can make our decoder faster, actually you can run the decoding on the CPU slower, and thus benefits from energy saving due to this decrease in the CPU core frequency. So here is the idea. A decoder must decode some pictures in order to display at specific presentation times, and the decoding must end before the picture presentation time. So at the end of between the end of the decoding of a picture and presentation, there is a slack time, which we can, if we increase the slack time, we can, which means we decode the picture faster, we can then reduce the power supplies and the CPU frequency, and in order to use less energy. So now, in order to achieve that, I need to give a bit more details about what does a decoder do, actually. So a video decoder reconstructs a picture from information it reads from a bit stream. So here's a typical block diagram of a decoder, and it consists of 4 main blocks. So first block, we've got the entropy decoder, which translates the bit streams into syntax elements, and those syntax elements are then dispatched to the wall, to every remaining blocks. So at first, we've got the partitioning. So partitioning is here to take care of how to match location on the picture and the bit stream contents, syntax element contents, and thus the picture is first divided into CTUs, and the CTUs is then split into CUs, and those CUs, which are small images blocks, are then going through prediction computation. So prediction computation, what's the aim of it? The idea is to predict some blocks, sample value from what the decoder already knows, so from what it has been decoding previously. So what does he have? He have local neighborhoods, so just previously decoded CUs. This is inside the same image, so we call it intra-prediction. And then we've got a previously decoded picture located in the decoded picture buffer. So previously decoded picture, we call this inter-image prediction. So in this prediction, there might be some error. And this is the aim of this block, residual computation. So basically, we are reading additional information and aiming to correct the prediction error we get here. This is why we've got a header. And so that the reconstructed block is the nearest possible from the original video we tried to transmit. And finally, we've got loop filters in order to make the picture prettier. So the idea is to refine the picture and then to fix compression artifacts such as blocking or ringing. So here is what a decoder was. So now what a modern CPU. So on a modern CPU, basically, we've got processing units which take instructions as an entrance from registers, and it exchanges with memory from cache and sometimes shared memory with other PUs. So on modern CPU, most of at least those I know, got multiple cores and able to work asynchronously. Sorry for my English. Asynchronously on different tasks. We will call this threads. And in this kind of asynchronous job, we have still to be cautious with concurrent access to shared memory. This is why there exists a synchronization mechanism. But shared memory here is hard to deal with, especially when we speak about dependent programs such as video compression, decompression. As an example, in inter-prediction, we need to, most often, you expect some data to be available in a picture in order to copy it and predict what the block value in another. So what happens when we have multiple threads running on it? So we've got the first decoder with no dependency, which has been running for a small time, so some pictures available. But on the second picture we decoded, we are a bit late inside the picture. And what we see is some pictures are trying to decode based on data they don't have. So the issue here is that we have to wait for prediction data to be available. So here we've got three decoders waiting for pictures to be available. So how could we use some VVC tools in order to solve that? The idea here is to have a look into VVC partitioning, but high-level partitioning. I'm not speaking into blocks, but more of how can we match some parts of the images and some chunks of the bit stream. So VVC gives us tiles and slice, which sometimes overlap. So you can have tiles with multiple slices or slice with multiple tiles. But overall, it all comes back to entry, which you can, in the same picture, decode without any dependence. So here is an example of what it permits. So if you remember the inter-picture dependency problem I presented earlier, here we're doing the same thing, but we're decoding small parts of pictures at the same time, and On the first picture, most of the area is already decoded when those threads were started, leading in less threading decoding time. Less threading waiting time, because all this area was already available. So here are some speed up result we measured on it. So no surprise, in all intra-profile, everything is independent. So we get high speed up. For 4 threads, we are close to 3.8. But what we notice here is in random access profile on a picture split this way, we got still a high speed up, and it decreased a bit for full HD sequences, and still and decreases again for HD profiles. So here are the first result. So now a second way into modern CPU to reduce the decoding time to decode faster is SIMD. So SIMD are single instruction multiple data. So a CPU uses instruction in order to manipulate data. Those data, this data is coming from registers, and in those registers, we can now have some on some architectures up to 512 bits registers, and since the CPU is operating on binary data, it can take those bits as vector registers and operate multiple computation at the same time. Here is an example of an addition. We've got a vector of 128 bits, and it's assumed by the processor that it will operate on 8 16-bit integer to make an addition. So this comes really handy when it comes to dealing with block computing, especially on the arithmetic operations on a samples value. And so that most of the tools we use in the different parts of the decoder, you can find here. So the transform, the intra prediction, and motion compensation, which is a predictor, and loop filters. Most of these operations are operations on samples, and thus have been optimized with SIMD. So another last consideration is that when we memory exchanges from the processing unit to the RAM may take some time. So because when running an instruction, the PU must load data to its register, and if the data is not available into the cache, it has to go look into the RAM, etc. So basically, what we thought here is if we are using less memory, if we make a smaller buffers into our decoders, we could reduce the cache misses and thus benefit from it. So here is a small insight on how we designed our rectangular entry decoders we presented earlier. So basically, intra prediction into the picture needs a bit of data around the current decoding CTU. So we need, with VVC, we need 4 samples left and 1 sample above. And we added to this buffer a sample line backup, so containing the whole picture, in which at the end of each CTU decoding, we store the last line in order to be available for the next line. And thus, just before starting decoding the next CTU, we are loading the previous line, so the above line of the CTU, and we can rotate this way and it saves space instead of working on a complete picture. And the last thing is in VVC we've got requirements due to IBC. IBC is intra-block copy, so the idea is just to copy some data in a previously decoded CTU. And what's interesting in this is that it uses a fixed size, whatever the CTU size given is. So in big CTUs, we will only have 2. But in with smaller CTU size, such an example for 50, we will get 8 CTU, and basically we are using the same principle than we used here at each run of the decoder. So here are some few results just to give an idea of consumption of a video decoder made on Xavier AGX, so NVIDIA Jetson platform. And what we see is that for a frequency of 2 gigahertz on CPU, we were consuming 5 milliwatts, and we were able to decode UHD sequences at 120 FPS. But what's interesting here is that we could still decode at 1.2 gigahertz and decode full HD at 35 FPS, which is a bit low, but still usable as video. And we only used 1.1 megawatts, so it's a 5-time reduction just by changing the frequency at a computational cost. So here is the end of the presentation. I'll answer a question if I wasn't to.
So thanks a lot for this presentation with very interesting results on your implementation of VVC decoder. So do we have any questions on the floor? So do we have anyone to help me with the microphones? Great. Thank you. So up there was a question.
Yeah, thanks, Pierre-Loup. My question will be about your last slide about your results.
This one.
Is it with a specific encoder configuration, or is it with a generic stream?
That's the question. Actually, those manipulations weren't done by myself, so I think it's with classical random access configuration of VTM, but I'm not sure. I could verify. Maybe Daniel can answer.
Thank you. The tests have been done with 2 values of a fixed QP with 27 and 37.
And what about the tiles configuration?
Yes, I don't have in mind, but
and the GOP structure and so on.
Yes,
my question is more generic. Was it a very specific bit stream for this kind of test, or was it something generic configuration of the encoder?
I think it was a generic configuration, but using tiles. Probably. I have to check.
Okay.
Okay, and yes, there.
And it's
please stand up and tell your name and the name of your neighbor who did not introduce himself beforehand. Thanks.
Okay, so my name is Alexandre Merca. I'm working at Temple University. Thanks a lot, Pierre-Loup, for your presentations. I have a question also about this result slide, and it's related to the title of the work, Low Power Video Decoding. When we are looking at these results, and for 8 cores, between these 2 configurations, you're able to reduce the energy consumptions by 5. But if I'm looking at the real-time capabilities, and if I'm thinking of the amount of data that you output, the ratio is much higher there. If we are looking like just the, it could be interesting to look at the average power per pixels, for example, and to look between these two configurations. What is the amount of power that you need to decode 1 pixels and see, because the difference between UHD 120 FPS and FHD 35 FPS is quite huge. The amount of data that you decode, the difference of amount of data that you decode is quite huge, but the average power difference, it's only 5 times. So did you look at this kind of?
Actually, those real-time capabilities, Colin, is just to say what we're able to achieve real-time on. It's not the sequence it was made on. I'm not sure. But it's still interesting because you spoke about matching those results per sample, and I think it's a great idea. But it's a great idea in order to compare decoders, actually.
Maybe just to give some word, yes, you are right. Maybe the efficiency is better when you are with Ultra HD instead of Full HD. And maybe this is due to the fact that with this kind of platforms, the static power is high.
Okay. Yeah.
So if you turn on the processor, even if you have a low frequency, you have a high energy consumption, because this is a very recent platform and with a very low technology. Very technology with a very small transistor, and the static energy can be high.
Okay, but yeah, I think it's also quite interesting to look at this kind of, if we're talking about energy efficiency, then let's look maybe per pixels also. And I had a second questions, maybe if I have time, about the slide just before. And maybe just because I didn't understood some things, but for this sample lines backup and the way that you are able to have this kind of sliding window where you store data and then you load them, I'm just wondering why you store and load if it's the same data and they're already here. Why you have to load that kind of data?
Actually, there is a in-loop filtering process which is not described here.
Okay.
And so that we need, we always need filtered and unfiltered data. And this is the unfiltered part. We need, as an example, IBC is.
Okay, but it's just the fact that I can see here in that row, store and load. And me, when I'm thinking of hardware, I think if you store and just load just after, do not load anything and keep data.
You could actually use instead of a sample line backup, you could use directly what was on the picture.
Okay, yeah. Okay, thanks. Thanks a lot.
Thanks. I think there was another question just behind you. Okay. Yes, another question. Would you please introduce yourself?
Yeah. So I'm Mathieu Muller from MediaKind. So I have another question. Could we foresee to port this kind of implementation on ARM or, for example, in recent Android TVs?
You mean test decoder on TV?
For example, yes.
We do have Android players running with OpenVVC. Actually, I have a GitHub I could share with you.
Yeah, but
it's
Android on
MPV.
Yeah, Android.
That was a question.
Okay. Okay.
Okay. Okay, good. Yes, is that clarified, that question? Okay, good. Thanks. Do we have any other questions? I would have, there's another one. All right, please, if we have enough time, I think.
Thank you. Daniel Sheen, again, thank you very much. Really interesting. Lots of it is very new to me, so my question may be ignorant. I've got two. One is, is there another reason to try to compress the duration for the decoding in time, besides trying to lower the frequency or any other in overall energy consumption from the perspective of the coding process? Could the time that you free up maybe use to do other bits? Or is it really, would you only pursue this technique for energy savings?
Yes, so if I understand your question is is it necessary to reduce the decoding time, or should we rely on more profile of what is sent by the encoder, so make a simpler decoding process to consume less?
Yes, I guess that you could take it into this direction. I think partly where I'm coming from is this observation that we are generally, when we're trying to reduce energy consumption on a software layer, we can distinguish between things we only do for energy and other other initiatives that we pursue for energy, but they have also a benefit for other characteristics like performance, quality of experience that is not energy related. Yeah. So that was my question. If this strategy of shortening the decoding time is purely a energy efficiency strategy.
Yes, because we are going. There is the assumption that the decoder doesn't know what the encoder sends to it, and it has to be a bit exact at the end. So, but of course, there exists some works into non-conformant video decoding. So you can disable filters. You can actually override the filters and make it disabled to spare some process and decode it at lower energy. I don't know if I'm answering your question.
Great. And then in the end, you showed final results of the power consumption for your NVIDIA platform. Do you have a comparison of a decoder that doesn't apply these techniques?
No, actually, I don't. Maybe someone has, but not me. I hope I could. I hope I could make some measurement on it, but
so
this is the reason actually we used this platform, is because NVIDIA provided us with some ways of doing those measurements.
Yeah, this is fantastic. So this slots right into the discussion that we had this earlier, right? Understanding what hardware is available to carry out measurements. So that this is really great. Am I understanding this right? OpenVVC as a decoder exists independently of the version that that you augmented with the new with the low power strategy that you implemented, or is this always baked into OpenVVC?
It's always been into OpenVVC.
Okay.
This is
great.
What,
so then this question of comparison, that I understand that you haven't got nothing else to compare it to. Okay, great. Thank you.
There are always there are others VVC decoders available, but
that would be interesting to see.
yeah. I'd like to, but the measurement do take some time, and I clearly lack it.
Yeah, if I may add up, I would also love to see similar things, similar values for an HEVC decoding. Of course, it would not be the exact same bit stream, but you could try to have similar settings, and that would also be interesting to see how they compare with, as he said, with other implementations that we have, and also OpenVVC, OpenHEVC, for example, to see how they relate. Or do you have an idea on that? Did you check that maybe? Or an intuition?
That's something we'd like to do, actually. But,
yes, okay. No, it's fine. It's a lot of work. But I've seen there's another question up there. Maybe the last one?
Yeah, so Gaël Ganbo from INRIA Bordeaux. So actually, it's more a comment about the previous remarks regarding computing efficiency figures. And I would like to say that, as I explained 2 days ago, I think these kind of figures can be really misleading, because what matters at the end are the absolute power consumptions. And why you will understand those results is that moving from full HD at 35 FPS to the other one consume 5 more times power, five more times power. And if you want to compute some relative figures, that maybe you could, I would rather use what Christian showed us this morning, and by comparing the gain of quality. So with 5 times more power, you would gain maybe, I don't know, 10, 20 or 20% of quality. Yeah, that's more a comment. But
Right. So I was trying to find a question. But, I agree. Maybe we should have gotten rid of this column actually, and just saying those were the consumption.
Okay, yeah. Thanks for the comment, and I think it's interesting to look at that. In fact, how that interrelates all. So with that, please let's thank our speaker again for this very interesting presentation.
Thanks for having me.
So next will be Olivier Lemeur from Interdigital. If you have not seen him before today, he's the second last speaker of today. He's the co-chair, the main chair. Sorry, I'm the co-chair. The main chair of this session, and we're very much looking forward to his presentation on. Can you please say the name of your presentation?
Energy-aware images.
Energy-aware images. Very much looking forward to your presentation.
Okay, perfect. Hello, everybody. It's my pleasure to make this presentation, our latest development at Interdigital. So I am Olivier Lemeur from Interdigital. And the title of this presentation is Energy-aware images. This project is funded by the Brittany region, Image and Réseau, and Rennes Metropole, and this is embedded in the collaborative project 3EMS2. So I have several slides for the context. I know that we have already seen this figure several times, but for the sake of completeness of the presentation, I have to go through just one time more, just before leaving and ending the workshop. So we know that the IP traffic has been multiplied by 3 from 2017 to 2022, and that in this traffic we have more than 80% of the traffic that is due to the video. And for your information, Netflix streams around 250 million hours of video per day, which of course is very big. And now the video streaming industry annual carbon footprint exceed that of the airline industry. So for sure, this is not sustainable at all. And we should add that for different reasons, such as the digital affluence hypergrowth, the new consumption pattern that we are digitally hungry, the business model of the big tech. So we have just a discussion this morning, and it was a part of the keynote last Tuesday. And of course, the energy demand of the current digital infrastructure. So in this talk, we want to reduce the energy consumption all over the, or I should say in the project I am managing, we try to reduce the energy consumption of the different components of the video chain. And for this presentation, we are going to focus on the display devices and most specifically on TV screen, such as OLED display. So we are going I am going to describe what we design, but just before delving into the details, so I have to remind what is the video chain in the streaming chain, but you know that, of course. So you have the production, you have the encoding, you have the distribution, you have the decoding, and of course you have the rendering. And there are many initiatives in order to reduce the energy consumption of these different elements in the chain. For instance, we are witnessing the rise of virtual production, which is very good since we are not, or virtual production are not affected by the weather, is not affected by the natural light changes and so on. We can reuse the assets and so on. There are more and more cloud-based solutions, and this is as well very nice since we can allocate just the amount of processing we need in order to perform the task that we have to do. So this is a very good point as well. We have new compression standard that would, for instance, VVC AV1, that would reduce the bit rate and then the transmission cost of a particular video. Of course, the energy consumption in order to make the encoding is increasing, but we encode once and distribute many times. So in this presentation, as I told you, we are going to focus on display devices just because viewing devices account for one of the most important sources of energy consumption in the video chain. So we had the figure this morning in the Samira presentation. This is more than 70%. Followed by data center, almost 20%, and for data transmission, sorry, for 20%, and the rest for data center. I didn't put the figure because it really depends on how we are computing and depend on the assumption and so on. But what we could say is that the viewing devices, especially a TV screen, are perhaps account for the majority of energy use. And what we have in mind is that if you can have a very small gain in this viewing devices, it would be very nice since considering the fact that there are more than 2 billion television deployed worldwide. And I just add a last comment at the bottom of the slide. Of course, this assumption just holds when the TV is on, of course. So what are the common consumption of the different viewing devices? So you have the table on the right part. So you have the desktop PC, game console, plasma TV, smartphone, smart TV, and you have the average demand in watts. So on the other side, you have the CRT TV for 19-inch screens that would consume 90 watts per hour. The LCD TV would be 45 watts per hour, and the LED TV about 32 watts. These figures are just average, and we have to be convinced that it already depends on the content. And we have made some experiments in our lab with a very big screen, and you see that the consumption of the different images from the left to the right. So on the left-hand side, you have a beautiful picture that would consume more than 100 watts. And on the right-hand side, you will have a beautiful picture as well, but that just consume less than 80 watts. So there is a very simple model that would rely on the energy consumption of all OLED display with the content, and this is the formula that you have there. Oops. It is composed of two terms. C is the static consumption of the screen, meaning that to get the static consumption of the screen, you just have to display a black image, just to switch off the different LED of the screen, and you will see how your TV is consumed. For this TV, we use in our lab, this is 60 watt, which is a lot, in fact, for a TV. And then the second term is related to the content, and especially to the luminance. And this is the sum of the luminance with a gamma factor. So you just have to sum the different pixel value with a gamma factor and being the resolution of the screen. Okay? So this model is very interesting, but it is very useful for RGB OLED. I will show you some example just after. And now if we can measure the power consumption, or at least have an estimation for the different content, we can perhaps try to optimize the different content in order to reduce this energy consumption with a particular constraint of quality of of quality, for instance. And at Interdigital, we have developed what we call energy-aware images, and this is a kind of definition of this kind of images. We would like to reduce locally and smartly the brightness of the image while optimizing the quality of experience. So we just want to reduce, finally, we want to dim the image in a way that this is more or less noticeable by the user, depending on the use case that you are going to use. So you have several examples on the bottom of the slide. On the left-hand side, you have the original image. You have 130 watts for this one, and we are going to reduce progressively the brightness locally and smartly in order to reach this one. Perhaps this is too much, but anyway, this is for the example. So we have a gain of 20 watts, and you see that we are going to dim the brightness of the image. So we have designed two different methods, in fact. This method are called PVR, pixel value reduction, and one is driven by the quality of experience, and the other one is driven by the energy reduction that a user would like to achieve. So the first one, quality of experience driven, in this context, we would like to guarantee to the end user a certain amount of quality. And this is very important for broadcast applications. So I am a broadcaster, I would like to guarantee the quality of the content to the end user. So this is the first use case. The second one would be more related to the amount of energy that you would like to gain. And in this context, we are going to guarantee an energy reduction while maximizing for this constraint the quality of experience. So let's say we want to gain 10%, 20%, 40%, and so on. And for that, this is well tailored for streaming services, we believe. So I'm going to the key point, sorry, the common point between these two methods are these things, pixel-wise dimming map. So we want to compute a pixel-wise dimming map, meaning that this is a map with a small amount of, that contains a small amount that we are going to subtract to the original image. So I'm going to go further into details in the second approach, energy reduction driven PVR. So we try to formalize a bit the problem. So we are working on the luminance. So you have the original luminance Y. You have a particular function here. This is a parametric function containing a number of parameters that are going to that will be used in order to define the attenuation map or the dimming map that we want to achieve. And you have the constraint. So Py hat is the power consumption that you want to have at the end user, and Py is the original consumption of the original content. And this value here is the percentage of energy reduction the user may want to achieve, for instance, 10%. So the key things is to compute this kind of, to determine how we can compute this function and how we can determine the different parameters. So we decided to use a deep network, but this is a shallow one, very shallow. It's not so consuming. I will explain just a bit after. We are going to use such network in order to determine the different parameters. Of course, we have some key requirements, memory frugal, energy frugal, and this should be a flexible approach. And this solution has been submitted to the next conference, ICIP. So, in more details, I'm not going to delve into too much detail with this deep learning method, but I would like to give you just an overview of the architecture we use. So you have RGB to YUV, you have the Y channel that goes through different convolution layers. You have a special pyramid in order to perform a kind of coarse to fine analysis in order to take into account the neighborhood of a given pixel in order to take a good decision. Then we have a number of feature maps that in output of this pyramid, and we need to choose the best one. So we have what we call channel attention. So we are going to put more emphasis on a particular channel. This is the same for the spatial localization. We are going to put more emphasis on a particular spatial location. And then we have, again, a set of convolution layer to get the dimming map. And finally, the dimming map is just added back to the original luminance in order to get the attenuated luminance. So this model is quite simple. There is less than 5,000 trainable parameters, so it's not that big. We have a limited number of channels as well. Okay. So the dimming map, again, is a pixel-wise map, and the value is in between -1 and 0. 0, you do not change the luminance, and -1, you reduce, you put to black, in fact, the current pixel. Okay, so now we have to train this network, and we use several loss functions in order to determine the best parameters. So we have 4 loss functions. The first two, the MAE, mean absolute error, and the SSIM are used in order to constrain the fidelity to the original images. And you have the constraint that you want to achieve. You want to reduce the energy consumption of the final image. In addition, we put another constraint on the way we are going to compute the attenuation map, because the attenuation map, we would like the attenuation map, a smooth attenuation map with very low transition, because we want that this dimming map should be easy to compute, easy to compress, and easy to transmit, and quite robust to subsampling. So if we do not have so much high frequency in the map, this is a very good point for the future transmission. So we use different, one data set of 30 images, 200 images for training, 100 for testing, and we use patches in order to make the training. So it's time perhaps to see some result of the proposed approach. So you have over there the original image, and you have several rates of reduction: 5%, 9%, almost 10%, 20%, and 30%. And you have the PSNR, so the higher the better. And for that, you have 38. So this is a good value of quality in terms of PSNR. But you will significantly decrease the quality if you go further in terms of reduction. Okay, so another example. So I hope you will be able to see this attenuation map with and without the total variation loss. So without the total variation loss, you should be able to detect some high frequency gradient and so on. And if you compress this kind of map, it will be quite expensive and not robust to subsampling. So this is why we use the TV loss, and then this one is much smoother. You have another example here of attenuation map for 5%, 10%, 20%, and 40%. And you see that for 5%, of course, there is almost nothing to, the reduction is very small, so we do not see the attenuation map is almost black. And of course, when you are going further, the attenuation is going much more important. And this is not the same for all the pixels, of course. So we perform a comparison with linear scaling. So you have 3 stripes there. The proposed method, the linear scaling. So the linear scaling, you just have to scale down the luminance with, this is a global approach. And we make a comparison between the proposed approach and the linear scaling, and the linear scaling tend to reduce too much the contrast. And of course, this is a global approach. It is not this is not efficient enough. Okay, another interesting result. This is on the horizontal axis, you have the rate of reduction, 5, 10, up to 60, 5 to 60, 5 to 60 for two different methods in green. And then you see that, and then you see that the model is not that bad, because if we ask for 5%, we will get 5%. If we ask for 10%, we will retrieve 10%. But the problem is that when we put the image on screen and we use a wattmeter and so on, this is not the same story, in fact. So when we ask for 5%, we indeed have almost 5%. But when we ask for 60%, which is not a real use case, but anyway, 60%, we just observe a gain of 30%. This is just because the energy model we use for the display is not at all accurate for the technology we use, because the screen here is not an RGB OLED screen, but this is an RGBW OLED screen. It means that for making a white pixel, in the former case, you have 3 LED to switch on. And in the later case, to make a white pixel, you just have to switch on one, the W. And this is why the current model is not accurate enough. Okay, just a short demo. So you have the original image with the consumption. And you see for this test, the static consumption, when you put a black screen, you will have 60 watt. So I'm going to scroll down now and to move from one slide to another with a certain amount of reduction, and we are going to see. So we start. So we request 5% of reduction, and we observe on the screen 5%. We request 10%, and we observe 8%. We request 20%, and we observe 13, and so on. Now I'm going back. I will go directly from one to the other to see that we really dim the image. Okay? Okay, so this is the main idea. What are the current limitations? So the display model has to be improved, and this is quite finally difficult to predict the right amount of energy that we are going to gain, since the model is not so accurate. This method should be used at the server side, and we should transmit the dimming and attenuation map all along the network. We are going to see that. So there are much more results in this two JIVET contribution, where we assess the impact of the TV setting, the ambient light. We use two screens, and we evaluate the cost of the transmission. So how can we deploy this approach in a video transmission? So you have the encoding, the decoding, and what we propose is to make a kind of pre-analysis. And in this pre-analysis, you are going to compute the pixel-wise attenuation map. This map is transmitted all along the network. We have some metadata in order to explain how to use this map at the decoder side. And this is, and you have a post-processing. So in more detail, this is this. You have the original video, the methods, the attenuation map, some details to use the map at the decoder side, and in the most use case, this is just a pixel-wise addition or subtraction. It depends on the scaling you use, and so on. So we just push all this method in a green MPEG standardization very recently, and we are going to, the contribution has been accepted, and we will going to make a new amendment to the green MPEG specification in order to not to make normative the method we develop, just to make normative the way we are going to transmit the information from the encoder to the decoder. So the way you are going to compute the attenuation map is your business, is not the business of the standardization. You can do what you want, but at least the framework will be normative, I hope. And okay, so this is a short conclusion now. So there are many initiatives to improve the way we use the this, but we need to reduce our energy consumption rather than be more efficient. This is the point. So thank you so much for your time.
Thanks, Olivier, for this very nice, interesting presentation on brightnesses. And we have even seen here on this screen, which is definitely not an OLED, that is, well, we can see differences, but it was still some quite nice pictures. So at least in this environment, I think it might work. I would be interested if this projector up there uses less energy, but I don't think so. Usually they have a very, very bright light inside, which does not care about the picture at all. But do we have any questions and remarks from the audience, please? Yes, over there, I see a hand.
So thanks, Olivier. So Mathieu Muller from MediaKind. What about HDR content?
Wow.
Does it work with HDR, or is it just for SDR? Or did you check with both SDR and HDR content?
Yeah, it works for HDR for sure. But I understand the point behind the question, in fact. So HDR consumes much more than SDR for sure. And we believe that we can have new technology in the coming years that will be able to reduce the consumption of HDR content with this one as well. We could use this one as well. So yes, we are working on this particular use case here.
And another question, what about the artistic content, the artistic approach and the legal approach? Because here you're modifying the original content and maybe some content owners don't want that.
So yeah, this is a good point. But we have two use cases. So the first one is the broadcast. In the broadcast, we are going to guarantee, or the broadcaster are going to guarantee the quality of experience, and then you can check whether or not the artistic intent is kept or not. For the streaming, it is another story, but there are several use cases in the streaming scenarios as well. So the first one is the user that is going to make the choice in order to reduce his own consumption. So in this context, we don't care about the artistic intent, unfortunately, but there is no problem of right over content and so on. Another use case would be OTT, when you take a representation, a particular representation, and with this representation, there is an attenuation map or a dimming map. And in this context, I think that we have to take care of the artistic intent, but it would be, for instance, Netflix that would define this attenuation map. And we come back finally to the broadcast scenario, I believe.
Okay, there was another question. I think Alexandre was first.
Yes, so Alexandre Merca from Temple University. I have a question about the, it's just an idea I get when I look at that slide. You are working at image level, so frame level, only taking account from one frame to another.
Yeah.
And I was wondering, could you extend that approach at a video level? Means to take into account the fact that maybe when the pixels have to switch from one intensity to another, you consume more energy than if you just change a little bit this intensity of the pixels and then try to minimize the energy consumptions also at this kind of at the video level with using the fact that the contents can be the same from one frame to another or can be different, and maybe trying to minimize the energy consumptions of the TV.
I'm not sure to get exactly the point, but we have tried to process video sequences, and it turns out that this is very stable, even if we do not make anything with the temporal dimension. So it was a good surprise, but in the future we would like to make a 2D plus T deep PVR solution, I would say. So I don't know.
Yeah, and I don't know about how it works, this OLED technology in TV, but do you think that it could be something that you could also take into account? The fact that from one frame to another, if you have to change a lot of the content, or if you can minimize the change somehow, or you could try to reduce the energy consumptions.
Okay, I see the point. So we are not TV manufacturer, so I'm not sure that
sorry.
they are happy with this kind of technology, by the way. So I don't know, in fact, how to manage the amount of light that you are going to emit for a particular LED over time. So no, I have no idea for this point. But thanks for the point.
Yes, thanks. Before you can have your question, Eric, would you already come here so that you can plug in your PC so that we have no technical problems after that question? So I hope it is okay that there is nothing
That's
related
fine.
to your... Thanks.
Thank you. Yeah, thanks a lot. Really enjoyed the presentation.
Thanks.
It seems to make so much sense to investigate such an opportunity. I've got three hopefully brief questions. The first one was clarification. You do transport the dimming map in order to make this individualized, that every viewer can decide to what degree to apply the dimming, because I would think you could also do it server side, or apply one setting for the broadcaster, and then you don't have to change the metadata.
Okay, yes, you're right. For the broadcast, for the moment, the framework we propose, we can transport several maps for one frame, one for 10%, for instance, another one for 30%.
Okay.
And it appears that we can make some interpolation between both in order to catch 20%, for instance.
Yeah,
So
okay.
it works in this context.
Yeah.
In the OTT and streaming services, if we upgrade the representation of the video with more data, we could have, for the HD, for instance, the map of 10%, the map of 20%, and then either the player or the user could select the best mode. For instance, we saw this morning the Echo player. We could imagine that there is another box, and you tick, I would like to use this attenuation map for the context, or you can use an automatic mode where the best map is going to be retrieved from the OTT or something like that.
Yeah. Great. So that's excellent. Now, your first slide said had the sort of the bigger picture. And I just have to say it because Samira also had in her opening slide, it said that 3.7% of internet traffic internet traffic is responsible for 3.7% of emissions. And I didn't make a comment then, but that's wrong, right?
Okay.
It's not the internet traffic that equates to 3.7% of global greenhouse gas emissions. Yeah, it's the ICT sector entirely.
Okay.
And again, you made a similar mistake. You said the video streaming carbon footprint exceeds that of the airline industry.
Yeah.
Again, it's the same, equating all of the ICT sector with video.
Okay. Good point. Very good
because
point.
if it's taken out of context, that might propagate.
Okay.
So that needs
thanks a lot for
adjusting.
pointing out. Yeah.
And then thirdly, you spoke about OLED. Is there any reason why this wouldn't work with LED?
LCD, you mean?
No. LED as opposed to OLED.
You should work with LED as well.
Great. Okay,
yeah.
Yes.
So there is more difficulties, I would say, with LCD because there is for LCD there is one backlight or several backlights,
Yes.
so we cannot manage the amount of light per pixel.
Yeah.
But we can extrapolate from the attenuation map several patterns. I would say the average value for this backlight, and so on and so on. And you can control the different backlight of the screen.
So these micro LED.
Yeah,
that would
exactly.
Be sort of a mix. Okay, fantastic. Thank you very much.
All right. So thanks again, Olivier. Please clap your hands for him. So I'm very happy to announce the final presentation for today by Eric Reinhardt from company called InterDigital. You might have heard that before, that company today. And we're hearing about media-related standards activities around sustainability. So, floor is yours. We're looking forward to your presentation.
Thank you very much for kind introduction and for letting me be here. I have many things to say. I think you've mentioned it before, but how many hours am I allowed to speak? There's no response. It doesn't matter. I will speak for as long as I want in that case. I have created slides a while ago, and I've created them largely for an audience that does not have your expertise in the area of sustainability. But I've kept at least some of these slides just to give you my view of things. Luckily, I removed the number of energy used by internet traffic just before coming on. I will start with this slide here. Can anyone tell me what's wrong with this slide? Let me tell you, it's an image. Yes? Yes, there's actually not a lot wrong with the pixels as such. What this is, though, is an image of the Arctic. And I don't know about you, but I like my Arctic white and not green. But you know, because of our lifestyles, this is the result of what we're doing. And so this is one way that I would highlight the importance of working against climate change, because that is what's happening up north if we use too much energy here. Closer to home, we're in a slightly different situation. It's more looking like this. This is Australia. This is actually an artwork that came out in 2013. I thought it was another good illustration. This is another situation we don't want. So how do you get there? So I said some statistics, and then I changed my slide. So now it should actually read some statistic. Here I'm preaching to the choir, so I will go very, very quickly over this slide. And in fact, I will just skip it for the rest. This is not so important. If you look at the life cycle analysis, the equipment that we use is costing energy, and that begins by digging a hole in the ground to get the materials. Then this needs to be clayed into some product, which is then shipped to a customer. And at that point, for much of the equipment that we use in our industry, for cars, for houses, at that point, you have used 50% of the energy that the equipment is going to use over its lifetime. Half already gone. So introducing technologies we have to be careful with. And then there's the use case, which is the other half. And then recycling is a very small percentage of the energy used during the life cycle of products. Now, the production, I have absolutely no expertise other than what I've just said. The use phase, that's with our background where we can do something, and that's where I would like to focus. So in the media industry, here's an image of roughly what we're dealing with. This is an intentionally complicated slide. No intention to explain every single block here, but you see, and the main point of this is that taking media from whoever produces it to the end user, who is then going to look at it, takes many varied paths. This could be a transmission network through cable, through satellite, through IP. Many ways to do it. They all cost energy. It's all different. And the main issue here is that not a single entity is responsible for the whole thing. This is a heterogeneous mess, I would say. And somehow we want to make this energy optimized. Now, how the hell are we going to do that? I've heard one person say at some point, well, I work for a big company, we make chips. We make our chips very efficient. So for this person, that was the problem solved. Now, I will make the argument that that is certainly a good thing to do, but it's not the only thing that we should be doing. We should effectively optimize this system, not the individual components. I'll get to that in more detail later. Actually, maybe not more detail. I'll get to it later again. There we go. Given that this was an introduction for a different audience, here another slide we've talked about at length. There's about two models that we can use. There's the linear model where we say more data is more energy, and if you then reduce that to zero, of course, then if there's no data, there's no energy. This is not the case. We've seen it from Daniel's presentation this morning already. There's still a lot of energy used, even if we transmit nothing at all. And that needs to be accounted for in our modeling. Now, the first model, perhaps okay for reporting purposes. Second model is a bit more accurate. There's still a lot of assumptions made, and the granularity of the knowledge is not very fine. We cannot say today, if I send one video from A to B, how much energy does that one video take? We do not know. If you want to optimize this system, you might want to think about how do you route your data so that it uses the least amount of energy. Well, we cannot even begin to think about it because we do not know the data at a fine enough granularity. What we do know is some high-level data. So this I got from Jens, who gave a webinar for ITU at some point, and I've reproduced some of his work. So thanks to Jens. The issue here is that if you look at streaming, the energy is used mostly the closer you get to the end user. The end user is actually using the most for streaming a video, especially when this end user is watching a television. Currently, if you take the average of all televisions installed, apparently that's using about 100 watts. The trend is in the wrong direction for televisions. For everything else, for the network, for the data centers, the trend is the capacity goes up, but the amount of energy used is about stable. It does need to go down, but at the moment, at least it's stable. With televisions, this is not the case because we're having bigger and bigger screens. I'll show you an infographic about this in a minute. We have higher resolutions, we have wider color gamut, higher frame rates, higher dynamic range. And all of that has an impact on the amount of energy that displays use. Luckily, there's entities such as Europe who are trying to somehow limit this. But to give you a flavor of the scale of the problem, if you put all the televisions flat on the surface, no, not all the televisions, if you take all the televisions in Europe, put them flat on the surface, what kind of surface area would you have? Well, I will tell you. In 2020, this was estimated to be about 242 square kilometers of screen surface in Europe, not worldwide. This comes from an EU study that's effectively motivating the limits on power use. This is growing. For 2030, this is projected to be almost 400 square kilometers. That's the size of Vienna. Apparently, and this is one of the things I've learned, that Vienna is a bigger city than Amsterdam. So, I've largely explained this slide. You could say we have this big, messy, heterogeneous system. Let's go and optimize every single component individually, and certainly I would not argue against it. Go ahead if you can do. But it's not guaranteeing us that we have an energy optimized system afterwards. So what I think is a systemic approach is what we need to be looking at. And now getting to the point where I'm having age problems. Yes. So the issue here is that we need to start thinking about what, if we spend a bit more energy here, can we save energy over there? Over there being the screen, because that's the big user. So can we, and of course, Olivier has given an example of how you could do this. You can say on the encoding side, whoever encodes, you do a little bit more, you go and make us a map, and then when you receive that map as an end user, you go and apply it, and then you use a bit less. Because there's a lot more end users than people encoding, this will save energy. And I am sure that if we think a little bit, we can find other ways that we can make this trade-off. And if we do it this way, we'll end up with a system that is more energy efficient, even if someone here needs to do a bit more to relieve the energy burden over there. So that is in essence my argument for standardization, because if we're not going to standardize, we cannot have this systemic approach. We have to do standardization now. So luckily, there's not thousands of people who are now looking at this as a result, but there are enough to have at least some inroads in this topic material. So the standards organizations that are relevant to video transmission are now basically all looking at the issue. Now, what I would say is they're not very far at this point. They're looking at the issue to see, is there something for us to be done? This is true for let's say, for DVB, for ATSC, for SMPTE, even ITUR at this point still, I would say, sniffing at the problem. Well, ITUR is actually relatively far. I will talk about it a bit more in a bit. But certainly DVB and ATSC, these are application standards. This is what a broadcaster would implement. These are based on standards that have the lower level technology underneath, such as MPEG and JVET. That's where the SCI messages go, where the itty-bitty detail is standardized. And then these application standards are saying, okay, that's a good technique there, I'll take that. There's a technique there, I take that, and then we make a toolbox, and that is then the DVB way of transmission. And so in Europe, we have DVB as the standard that's being followed for television. In the US, it's ATSC, for instance. So it's important that these standards bodies are looking at the problem, because eventually it's them that decide what stream of information comes into people's homes. So the way to standardize energy efficient technologies is you need to first go to MPEG to get the low level stuff standardized. Then you need to go a step higher up. You go to DVB and you say, look what they've done over there. Can you standardize this? And so you cannot go to one standard and have it over with. You need to be everywhere. So that is also our approach. I'll show you a slide about that a bit later. But first, I will not replicate what Olivier and Christian have discussed before, and the VVE low codec. I will not go back into detail there either. I'm not qualified. But these are already examples of standards contributions. So I will start with ITUR and ITU-T, largely because that's where I'm most involved. I need to mention ITU-T study group 5. So the ITU has three divisions, the T sector, the D sector, and the R sector. Relevant to us are the T and the D sectors, no, the T and the R sector, sorry. And within that, there are study groups. Study groups, the two that are relevant for our line of work are ITU-T study group 5, which is on sustainability, circular economy, and everything that goes towards basically a greener planet in terms of telecommunication. So they have worked a lot on data centers. Now, this is slightly outside my domain, so I note that I'm not doing justice to the ITU-T study group 5 by saying they do data centers, they do more. But I'm not an expert. But if telecommunication is your domain and you're interested in a lot of work that has happened, go have a look there. There's interesting stuff there. Where I'm active is in the broadcasting standardization specifically, and that happens in ITUR study group 6. And then what am I saying about that? Here we go again. Yes. So I did remember that. So a couple of years ago, we decided, as we being InterDigital, as a company, thinking, okay, we are already active in I2R Study Group 6. We know about standardization there. We are known, we are respected. This is, of course, the best place to start standardizing any of our new research because we are taking seriously there. Unfortunately, in standardization, it's an investment of multiple years before you can actually realistically start having a voice. It takes time to convince people that what you're doing is for real. Now, we've done that work in the space of HDR, so we're in a good shape. And so now we're trying to push sustainability there. Of course, ITU is a United Nations body for telecommunications, so that means that it's not a fast standardization organization. So after a couple of years, we are gaining momentum. We have already a few documents out there. What's good about I2R, at least, is that all the documents are freely available online. You can go and find them and download them. So all these numbers there are the pointers towards these documents, in a sense. So first one we ended up looking at is well, an opinion, in essence. I2R has several documents, opinions, there's not many of them, recommendations, which are normative standards, and reports, which are information documents, non-normative. Now, an opinion is basically saying, we think that this is how things should happen. And the 104 is an interesting one, because ITU is now saying, try not to do carbon offsetting, because we were seeing that carbon offsetting is a cheap fix for deeper problems. So in essence, it's not even anything to do with telecommunications, but we have created an opinion. I'm actually quite proud of that. In no involvement from my side, but certainly BBC has contributed a very interesting document to ITUR BT 2385. This is a document that is discussing the energy requirements of broadcast systems. Worth a look at. And then finally, about a year ago, as part of the rapporteur group that I'm happy to co-chair, we had a webinar. This webinar is on the website, can look at it. And we had 3 speakers, one from Arte, a French-German broadcaster who are quite far advanced in their efforts to go green. Another from BAFTA. They have what's called Albert, a carbon calculator for production. So if you're making a movie, you can have your movie certified to be low carbon, in essence. And the carbon calculator for that and the certification process is called Albert in the UK. There are others, but this is, I think, the one that's most well known. We had a presentation from that. And then finally, we had Jens Malmoden discuss his latest data on energy use in transmission systems. Now, we have since worked that into a report, which is available, and that's called BT 2521, very recent edition. So I'm going obviously in far too much detail here because I know this stuff most. Stuff I know a bit less, and I feel slightly uncomfortable talking about because the chair of Green MPEC, or one of the chairs of Green MPEC, sitting right here in front of me. But Green MPEC is one of the standards that we do want to seriously look at. It's out there. It has effectively a small toolbox of technologies there to help reduce the energy effectively on the decoding side or on the display side. Now, I don't really want to go into too much detail because we've already discussed. But in well, the topics are here. One of the things that I've not seen discussed so much today is the media selection idea. So in streaming, currently there's streaming ladders that say basically we have a content, we are going to encode it many different times. And then in MPEG- or DVB-, you can then, as a receiver, select which of these streams you would want to receive. And normally, this is used to manage bandwidth issues. And bandwidth, if you're in a low bandwidth area, you're dropping down to a lower quality stream. But why not use that for selecting a stream that fits your needs for energy use? A very good idea. Not yet in an application standard, but it is in Green MPEG. Very good stuff. So Green MPEG is effectively the oldest standard that I know of that deals with the issue of energy. New ones are very, very much needed. What I wanted to show you, the second last slide, is the role that we're playing, and we being InterDigital. So this is effectively our strategy for standardization. We're trying to be a bit everywhere. And the reason I have already explained, we are not going to be able to actually make an impact on the world if we're not trying to push everywhere. We need to. So in I2R, that's where I've been pushing and prodding, starting to be successful. In MPEG, it's Olivier who is pushing his contributions. In DVB, I'm co-leading a study mission. This is the DVB way of saying, is this new topic interesting for us? What can we do? And so this study mission is this month coming to an end. We're going to advise DVB that, yes, indeed, you should do more. And a report is forthcoming, which hopefully is going to be published at some point. Now, we have a colleague in the US who has just started chairing a similar thing in the UHD forum. There's a sustainability committee. They're looking at Ultra HD and how can we make that more sustainable, useful exercise to do. ATSC is sort of the American version of DVB. They are a little bit behind. They have also just started to form a group, and we've taken well, my American colleague has taken a leadership position there as well. And then SIMTI has a working group on cloud and sustainability. Very interesting. They have it's a slightly different angle because it's not strictly broadcasting, but it is certainly touching upon everything that we need to do. And this group has produced a paper that I don't know if it's paywalled or not, unfortunately. But send me an email if you want to look at it. I'll see what I can do. And then finally, there was some contribution also from Olivier on an SCI message earlier in JVET. I think it came up in your presentation. So for the future, where this is heading, well, most standards bodies are looking at the problem. That's obviously not enough. Acting is much better, but at least it's on the agenda everywhere. One of the things that I think needs to happen quite urgently to be able to optimize the system, but also to be able to give the end user choice, is a fine-grained measurement. So every video that comes into someone's home needs to be annotated with how much energy is this using right now, right at this moment. If we have that, we can start to optimize this system. And the last point. So yes, we've seen that displays are a relatively big problem, becoming a bigger problem. I hope that CE makers take note and start acting. And then what was my last point? Yes, I think there's a lot of mileage to be had out of effectively tinkering with the content, so that the moment it ends up on a display, it causes the display to use less energy. So Olivier's presentation was an example of it. I am not aware of other examples than what we're currently working on, but I do believe that if we sit down and think a bit more, come up with other ways to do this. And of course, that is ideal standards fodder, because it says we're going to process here and we're going to save energy there. And for that, you need standards. And that's me. If you make your questions short, then we can finish this thing quickly. Huh? Yes, thank you very much.
Thanks a lot for this very, very interesting talk and a lot of insights into standardizations and stuff. Before I hand over to that question, I would have one maybe challenging, mean question. Do you think standardizations are sustainable and efficient? So standardization efforts and how that is done, how standardization bodies work?
Well, they're thorough. Not necessarily very quick. Maybe I'm not fully understanding your question. Is it the process of how a standard
I mean, what I noticed is, especially before COVID, a lot of people were traveling to one place from all over the world. And that is also quite something where one could think, is this all really necessary? So it's going in this direction.
Well, I think DVB is a little bit ahead there, and they have started to do things at distance more and more. But at the same time, there's still no substitute for occasionally meeting each other to make progress. You can't completely get away from it. But yes, there's a lot of travel involved. As they say, you need to spend money to make money, but maybe we need to spend energy to save energy as well. So I don't know exactly where we stand.
Okay.
It was not so mean, the question. You can do better. No?
Okay. Thanks. I'll try next time. Yes. Next time I'll try to do more. Okay, there was a question up there.
Yes, I have a question about standards. Usually when we talk about standards, especially in video, we have to talk about patents.
Yeah.
So I was wondering if the patent issue is addressed there, on if there are plans to have, at the same time as standards, reference implementation or open source reference implementation in quality integrated in that, or we are still in the old world where we define standard, we have still patents locking some part of it on non-real common implementation.
Yes, I'm certainly working for a company that makes licensing its business. And I think personally, by itself, this is reasonable, because we do a lot of research, and at some point we would like to have bread on the table. What happens normally is that we end up with licensing statements. I'm most closely involved with ITUR, and we have a blanket statement that says, and you have to have, because otherwise you cannot work in ITUR, that says if this becomes a recommendation, then there needs then this work, the idea needs to be made available equally to everybody, but it's not necessarily free. How this works in other standard bodies, I
have another reference, which is HPC. So I work in HPC, and there are standards, of course, strong standards for OpenMP, MPI, and outside several others. Usually there are no patents there because business models are more related to hardware. So perhaps a shift in business model on your side, on this side, could have an influence, because the patents is clearly a limitation in first the distribution of the standard. Secondly, to find new way or to reduce the global impact. I know in HPC it's done in another way. That's all. To answer your question.
Yeah, you're right. I don't think I have enough impact in my company to change a business model, but yes, these are political questions that I don't really know the answer to be completely honest. Sometimes there's issues with patents. That's true, and it's unfortunate. Yeah.
Okay. Any more questions? I see a hand up there.
Thanks a lot. Really very interesting talk. And I wanted to briefly ask, what do you think the role of the regulator is? We mentioned before the EU is tightening constraints on device lifetime through making it mandatory to provide updates for 5 years. And there was a debate around the new stringent energy criteria for 8K televisions with big outcry by manufacturers that they couldn't meet those tighter criteria, so practically excluding 8K TVs from the European market. Do you think that is sufficient? I would hypothesize that manufacturers, they have a very strong interest to participate in the European market, and innovation will ultimately result in reduction of energy consumption. So this it seems that the European Union with the Energy Using Product Directive, they are really tough. Do you think this will do the job to bring down energy consumption? I mean, the dimming approach that you had is really complementary to this. Yeah, so that's fantastic. But yeah, if you have an opinion on this, it'd be great to hear.
Yeah, we're not display makers, and are there display makers in the room? I didn't think so. So I can speak freely. Yes, absolutely. It's a question of a carrot versus a stick, and I think especially with any quest for moderating, for reducing, for toning things down a bit, eventually humans, it's in their nature, it's very difficult to make someone use less, even if it's available. I can grab it, I can touch it, but I should not use it. It doesn't work that way. We need a stick. And I think these EU regulations are marvelous. Personally, I think 8K televisions are by themselves, by their nature, problematic. There are far too many pixels. The pixels become so small that it becomes really difficult to create the light, and that's why the energy is going up. It's lunacy. No, give me fewer pixels, and I'll be happy with it. So, 8K. As far as I'm concerned, the only reason 8K exists is because it's easy to manufacture. It's not a great market demand for 8K. So, Europe seems to have picked up on this, and they're basically saying, okay, hold on a bit, but go do your homework before these displays can be on the market. Actually, I've read the regulations. It's not saying that 8K cannot be on the market. It's just saying a television of this size should not use more than X watts. That's all they're saying. And it just happens to be that with an 8K technology, you cannot meet that requirement. But I think it's good. Yeah, it needs, yes.
Thanks a lot. Any more questions from the audience? I think it's really interesting discussions. We are facing a lot of different facets of this problem, of regulations, of standardizations, which is interesting to see, and actual implementations. So anything else from your side? Okay, then I think do we have anything else on the agenda? Well, then at the end, it's just for me to say thanks a lot for taking part. Thanks a lot to the marvelous speakers we had. We had some very, very interesting talks with a lot of different insights and ideas. I think we will all stay here for another coffee pause. So if there are any things for discussions or to talk to people, I think it's really interesting. It's a great occasion to talk to them. It's not easy to see them and to gather them all at one place. And with that, thanks again for taking part. And yes, I wish all of you a good journey home. And do you want to say something, Olivier, as main organizer? Thanks to you, of course, for asking me to be co-organizer here. It's absolutely a pleasure, and it's really nice to meet all of you. And I'm really happy with the talks, and I learned a lot this week and this day. So thanks, and enjoy your day.
Thank you.